finish up the dying handout, we'll be looking at the mass spec handout. Mass spectroscopy. Where's the dying handout? Were there any other questions or any questions about this page here? How we do on those? The answers were posted. Were there any, there was an answer key in the packet. Were there any questions about these? How'd you do on those?
On the one about, I just wanted to ask you that, the ring.
Speak a little bit louder.
So the second one from the bottom, the HCl with the ring, how do you, like, what's the best way to go about determining where to form a carbocation? Like, I would assume that you would form it in the ring where it's tertiary substituted as opposed to the exterior one where it's disubstituted. But that's not right.
No, you have to look at the resonance structure for each possible cation.
Okay.
You're always going to form it in the middle. You're always going to make a resonance stabilized cation. For example, if you reacted over here, you make cation there. Why? Because it'd be resonance stabilized. And so we can show H plus, this reacting this way, and this would give H there, plus there, resonance stabilized, and so you can show resonance structure. And you would get that there. Is that correct?
No. Can it be some substation number?
Why is that not correct?
It says, in the answers, it says it's not correct.
Do what?
The answer says it's not. Couldn't you make, shouldn't you?
I'm doing this here first. I'm reacting this alkene. Is that correct? This alkene?
Yeah.
Okay, and that's tertiary, and this is primary. Okay, what if we react the other alkene? We're going to leave cation on the left. I'll come this way. Boom, boom, new H out there, and a plus here. Then these electrons can windshield wiper over that way. Boom, boom. That look right? This is secondary. This is tertiary. That's one cation. It's got characteristics of secondary, tertiary. This is one cation. It's got characteristics of primary, tertiary. Which one's better? This one. So forget about that ray up there. That's why that ray is so good. It's a better cation. You've got to go through that process to find out this is a better cation. Now, we're heating. So which product are we going to get? The more stable. Do we want chlorine bonded here or there? If it's bonded there, you got a tri-substituted alkene. If it's bonded there, you have a tetra-substituted alkene. So the chlorine's going to end up bonded here. Product shown, it should have a chlorine bonded right there with double bond in the ring. Is that right? There you go. You got to look at both alkenes. Consider the resonance structure. Right? Anybody got an extra terry cloth towel on? Mine's kind of saturated with ink. And for some reason, the board has gotten quite terrible this week. Not good. Okay, last questions. Any last questions on the 1-2 versus 1-4 additions? We're looking at dienes. We're only going to be reacting them with like HX, HCl, HBr, etc. You've got your thermodynamic product that you get with the heat. Cold temperature gives the kinetic product, which is 1-2 product. Thermodynamic product is not always 1-4, sometimes it's 1-2. You determine that by looking at which is the most stable product. Basically, we're using our knowledge of resonance, because we've got resonance stabilized cations that we're dealing with. Any other questions about that chemistry? Okay, let's look at the next topic in this handout, which is Dielsalder reaction. Dielsalder were chemists who won Nobel Prize in 1950 for this reaction. The Dielsalder reaction involves a diene reacting with an alkene. And we're going to make a ring here. We're going to make a cyclohexene. Cyclohexene. I'll try to get us so we can see this. This is called the diene, obviously. This guy is ended up going to like dienes. If he likes dienes, what do you want to call it? A dienophile. So the alkene is called a dienophile in this reaction. This reaction is also known as a 4+2, because that's 4 carbons and this is 2. And 4 plus 2 equals what? 6. It's a 6-membered ring. Okay, all Dielsalders are 4 plus 2 is 6. You see 3 pi bonds here, you only see 1 here. Thus we're making 2 new sigma bonds. This reaction is thus thermodynamically favored because we're making stronger bonds. But it's not entropically favored because you got 2 molecules coming together to make 1. Really need some paper towels. Well, I'll use all the white space we have here. Really, this reaction is an overlap of p orbitals. Sounds like resonance. You draw your diene. Don't we have 4 p orbitals? Yeah. There, you can make 1 electron in each. Pi bond here, pi bond there. Of course, there's p overlap between 2 and 3 also. The other is also a pi system. 1 electron there. There's your alkene. Essentially what happens is these two come together, and as they approach each other and start reacting, these p orbitals start interacting with those p orbitals. And those start interacting with those, and you get this sort of cyclic array of p orbitals. And that really leads to the reaction. And I'm really not going to say much more about that other than just sort of telling you, hey, we got p orbitals coming together and sort of overlapping. Now, typically, your arrow movement for this is shown something like this. You can start anywhere. I'm going to do 3 arrows, I believe. You can start anywhere. I'm going to start right here. These electrons sort of windshield wiper over and go bond over there. So we sort of do this. Well, something has to leave that carbon. It's already got 4 bonds. These electrons leave and go up and bond here. Well, something has to leave here. Well, these come down and replace what left. And And all that arrow movement right there, if you can see that and understand it, gives that right there. Because when this comes over, we're making that sigma bond. When this comes up here, we're making that sigma bond. And when these move down, what are we making right there between there?
Double.
Pi bond is just there now. So that's your typical arrow movement for your 4+2 Dielsalder reaction. This became a very big, great way of making cycloalkanes, specifically cyclohexanes. And lots of compounds, lots of natural products contain cyclohexane rings, especially like your cholesterol ring system, which contains 3 or 4 cyclohexane rings. So it was very big in making natural products, and that led to these two getting Nobel Prize. Okay, so that arrow movement is going to show below, coming up there. You can also do this. The dienophile can be an alkyne as well. You do this with an alkyne here. When you zip it together, boom, boom, boom. When that moves up, you're still left with one pi bond there. So there's a pi bond on both sides. This is called a cycloaddition reaction. Basically, you're adding things together, and it's cyclic. It's a cyclic transition state, sort of shown like this, and you get a cyclic product. So a cycloaddition. That is a general type of what's called pericyclic reaction. Your pericyclic reactions all have a cyclic transition state. You can probably look these terms up in your textbook or on the wiki. Okay. You can also have some heteroatoms in your diene or alkene. It wouldn't be an alkene then. But you can have heteroatoms involved. We won't really be doing any of those here. But in your advanced chemistry, you see like nitrogens and oxygens in your Dielsalder. We're mainly, I believe, only going to be looking at carbon and thus making carbocycles, rings with just carbon. Okay, in the examples up there, especially the one with the arrows right there, both are symmetrical. We can have other dienes. It's like something happened to this board. First off, let me note this. Your diene has to be in the S-cis conformation. What is S-cis? Well, that's S-cis and this is S-trans. It should be written there, right? Written there? What's the difference? Well, there's no change in the double bond. It's the change in the single bond. This stands for single bond. About the single bond, there's cis. Because if you look at that single bond there, both alkenes are on the same side of it. Where if you look at the single bond here, one alkene's over there and one's over here. That's called S-cis, that's called S-trans. Hopefully it's quite obvious that for these to zip together like that and the 4 to bond to the 2, they have to be like this. Okay? Now this guy can actually rotate back and forth. But it has to be in this to react. Now we're going to see some non-symmetrical dienes. There's a methyl here but not here. These are just some examples. I took some of this from the web. These are important. These rings. Your diene can be in a ring. These are actually very reactive in the Dielsalder reaction. Why? Because they're stuck in the S-cis form. You see, these double bonds are both this way. They cannot rotate and one go the other way because they're stuck in the ring. So they're always ready to go. And That makes them more reactive in Dielsalder. Now, at the introductory level, you're always shown your diene like this, and that like that, with big neon signs. 4 plus 2 is 6. Okay, word of caution. Your diene is not always going to be drawn like that. It could be drawn like this. Okay? This screams Dielsalder. But if you saw these two, you got to know, hey, well, I got a diene here. I can rotate this and draw it like this. Now it looks more like a Dielsalder. Okay? Now your dienophile, which is your alkene, that's your 2. 4 comes from the diene. The 2 comes from the dienophile. Those typically have a nitron with drawing groups on them. In all these you have alkene, 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 alkene. Then you have the drawing group, typically like a carbonyl group or nitrile. This has 2 carbonyl groups. This is a condensed ester. They can be cis or trans about the alkene. The dienophile can also be in a ring. So if you see this, there's your 2 right there. And then I mentioned you can also have an alkyne can be there. Let's look at some stereoselectivity. Again, guys, I apologize for the board. I'll see if I can figure out how we get it back workable. Everything's in front of you. Stereoselectivity. Show you what I'm talking about. You take this diene, this dienophile, you zip them together. 4 plus 2 is 6. You're going to get to 6. There will be a pi bond there. Okay, when you do your mechanism, this comes down, pi bond there. But then you got to have these 2 groups there. Note that these 2 carbons are now tetrahedral, where originally they were trigonoplanar. Okay, since they're tetrahedral, you have choice of forward or back. This is going to be cis. Why is this cis? Because you started cis. Okay? The Dielsalder is very stereospecific. Stereochemistry that is in the starting materials is often always maintained in the products. That's because there's no intermediate in the reaction. It's just a transition state. Everything's cis, boom, it takes place, everything's still cis. Now on the other hand, if you take this and you take the trans version of this, you'll get the trans version of that product. Now let's look at the diene. This is a diene with 2 methyls, and that's an alkyne. You zip this together, boom, boom, boom. 6-membered ring. There should be pi bond there. You should also have one here because there's one left over here. Note that these 2 carbons are tetrahedral, and since we got 2 substituents, they can be cis or trans. They're going to be cis. Why? Because your alkenes were both the same here in terms of E or Z. That isn't E alkene, it's trans. That's trans. Basically, they're both E. They're both the same, and so they're going to be on the same side. Now this takes some deeper explanation and like me showing some models to see this. Up there is a little bit more straightforward. I'm not going to take the time to show this and all the modeling of it. Okay? So it's just sort of like, hey, look at your 2 alkenes. If they're the same, the groups on these carbons here are going to be the same. So just giving you a little flavor of the stereospecific nature. But on the other hand, this alkene, that's EE, this is EZ. Now that alkene is stuck as Z. single bond can rotate and flip that and make it S trans. We're not going to change the actual stereochemistry of the alkene. So this is E and Z, it's opposite. That gives the product that they're opposite or trans. Okay? Again, if you want to see really how all this takes place and the modeling of it, that's sort of a little bit beyond the scope of what we're going to do right here. But that is some of the stereo specificity or selectivity that's built into a Dielsalder. Let's skip the next page. Now let's do some more examples of the stereo before we move to the regio. Some of this is just repeat. I think the page we were looking at I took from the web, and like this is my page. That's just basically a repeat of before. Let's look at some examples down here and then we can do some. This here, 4 plus 2 is 6. You got two ester groups here and here. They're going to be trans, right? Why? Because they're trans about the alkene. Okay? Of course, tonight you're going to go home, you're going to zip these together, you're going to cover this up, you're going to show the product, you're going to say, oh, that's right. Okay, things like that, yeah? Yeah. Because what I'll see is on quiz day, we'll see this, and these groups will be over here and everywhere. Don't do that. Go home, practice the reaction, see what's going on. Okay, 4 plus 2 is 6, but there's more to it than just 6. Because when you're asked to show the product in 10 seconds, that's when it's like, okay, not quite as easy. Let's see. Plus an enantiomer, right? This is a chiral product, right? No plane of symmetry there. Show the product of this one. Yes. Those were sitting there the whole time? We'll see if they do. It's just not. I've done this before, and it like just become real clean, but I don't know what. It's not doing it anymore. It's like it's been cleaned with something that wasn't supposed to be cleaned with. I don't know what happened. Okay, this is a diene. This is E. This is Z. See if we show it in the S-cis form. We've got phenyls on each end. Phenyl there. That'd be E. Phenyl there. That'd be Z. Sort of gets in the way there. Then we got this here, the electron withdrawing group. Ultimately, we'll say this. If either one of your reactants is symmetrical, you don't have to worry about regiochemistry. We haven't done that yet. Basically, you can draw this with the CN up or down. It doesn't matter how you position these. You can position them like that or you can position them like that. It doesn't matter if at least one of them is symmetrical. Symmetry doesn't count for the E and Z. This is symmetrical. Because it's 4 carbons, there's your diene, and there's a phenyl on each end. You zip this together, boom, 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 and we're going to get a 6-membered ring with a pi bond here. There's a phenyl here and here, and a CN here. What's going to be the relationship between the 2 phenyls? Trans. I'll draw one bolded. I'll draw one dashed. What is this going to be? Is it dashed or bolded? That we cannot predict. What I showed you, we can only predict this versus this, or this versus this. We cannot predict that versus this. So it really gets complicated here. I can show this is dashed in bold. I'm only going to show one product here, but basically that's it there.
Would there be or would it be a dash?
Well, since I'm not showing any stereochemistry there, it's hard to discuss what an enantiomer would look like. Okay, cyclic dienes. Here we have a cyclic diene. Here we have our dienophile. What I'm going to tell you to do with these is just ignore the cyclic. That's a 1 carbon bridge between the 1 and 4. It's a 1 carbon bridge. Doesn't matter, just ignore it. Zip this together. I'll come this way. What do you get? 4 plus 2 is 6. There's your cyclohexene, which every Dielsalder gives. What do we got? A cyano here. That would be it except for this 1 carbon bridge. The 1 carbon bridge is still there. Let's just draw it back. Where is it? It's between, if you number this, that's 1, 2, 3, 4, 5, 6. Okay? 1, 2, 3, 4, 5, 6. The 1 carbon bridge is between 1 and 4. It's still there. So we can just draw it in like that. Connect this a little bit better. It's still there. This looks a little bit like what from left? Norbornene with that ring and the bridge. Yeah. So whenever you do these, when you have a bridge and you're here or there, just do your 4 plus 2. Forget about the bridge. And then draw it in when you're done. Okay? Let's do the one below. One below the bridge is an oxygen. It's actually called furan. But it still reacts as a diene. So there's your 4, there's your 2. So show the product of that. How's that look? Just got that oxygen bridge between 1 and 4. Zip it together, boom, boom, boom. Now there is some stereochemistry here, but it's beyond what we can do because we can only do those and these. A lot of times you could draw your bridge kind of bolded. Really don't worry about that. Pretty much has to be. I mean, if you got a bridge, it can't be like this if it's going to be a bridge. That reaction right there is used to make Tamiflu, ultimately.
So it has to be bolded? Or?
Now it could actually be dashed. Tamiflu is shown on the front, on the very front, top left. See Tamiflu? Which drug looks like it could be made from a Dielsalder? Tamiflu. It's got that cyclohexane ring in it, right? Right? Ultimately, for Tamiflu, this oxygen, the bridge is actually opened up. And the oxygen that's bonded to that kind of pentyl group is that oxygen probably. Here's the ester group that's over there. And then they get the other groups on there by doing some alkene chemistry. It was also shown on the page. How about a cyclic dienophile? Show the product of the one here. Cyclic dienophile. Every Dielsalder gives that right there at least. What else is here? We got groups on here. Draw that a little bit better. Are they cis or trans on the alkene? Cis. They're going to be cis here. Because these two carbons are now tetrahedral. Five-membered ring, these could be trans. But because they're cis there, they have to be cis there. But because they're cis there, they're cis here. So you get that plus what? Nope, there's no enantiomer in this compound. This compound has a plane of symmetry. There's no enantiomer. Right? That product's achiral. Plane of symmetry. If you drew them both back, it'd be the same compound. Do what? How can that be trans? Well, it's not going to be from this reaction, but theoretically, I mean, a 3-membered ring can't be trans, but a 5 or 6 can have trans.
Oh, like chair. There could be twisting.
It is theoretically possible to have that, I believe. But it doesn't come from this product. This product is going to be, they're going to be cis. What's the product of the reaction below? You got this cyclic diene. 2 rings there. What's product there? I know somebody's thinking it. Go ahead and say it. No reaction. Why not? Can this is stuck in an S transform. Can it rotate to S cis? No. I can't do Dielsalder. No reaction. On the back, one of these shows Tamiflu synthesis. They do a Dielsalder. They actually show some stereochemistry, exo versus endo. If you remember those terms, those are diastereomers. Those can be separated. Ultimately, they get to Tamiflu. Lots of unique chemistry here. In a couple of weeks, we will see something called a tosylate. They use a mesylate, which is very similar. The other is pretty advanced chemistry that we're really not going to see. On the back is a neat reaction that's sort of like a Dielsalder. You all know the inflammation process from prostaglandins. Prostaglandins causing inflammation, etc. Coming from arachidonic acid. You all know that, right? Right? Yep. Talked about it today in biology. And how aspirin acts as a drug. How does aspirin inhibit inflammation? Aspirin inhibits the synthesis of prostaglandins. There's a variety of them. There was actually one on test 2, and it had 128 stereoisomers. Okay. Synthesis of prostaglandins comes from arachidonic acid, and one of the first steps in making them is to react arachidonic acid with oxygen. Oxygen can be drawn like this, like an alkene. And the 2 double bonds on the end sort of react. These react here, these react here, and this goes up here. It's not exactly like the Dielsalder, but it is a pericyclic reaction with a cyclic transition state of p orbitals. So it's somewhat related. It's related enough that I can show you how this all happens, and you know how aspirin works. You get this odd-looking cyclic peroxide. The enzyme that catalyzes this is called cyclooxygenase enzyme, or COX. You've heard of COX-1, COX-2 inhibitors. Some of your anti-inflammatories are selective for one of those enzymes. Well, they're inhibiting this enzyme. You inhibit this from happening, you inhibit the synthesis, ultimately, of prostaglandins. And so that's a cycloaddition with oxygen, but it's not exactly a Dielsalder. You can look at the arrow movement. I think I got it right. To see there's no pi bond that's here. It's a little bit different. Prostaglandins can also affect like blood aggregation, and so aspirin, if you inhibit that, you make the blood thinner. If you inhibit aggregation. So aspirin can act as a blood thinner by the same similar mechanism. So that's Dielsalder. Should be some questions in the workbook for working, and of course in your textbook. Any questions about Dielsalder? One thing to remember at the beginning is 4 plus 2 is 6. Time to look at mass spec. Mass spec is obviously from the name. What does mass spec tell you about a compound? Mass. Okay. IR tells you roughly functional groups. Mass spec tells you mass. Very important, right? If you had an unknown compound, for example, if we didn't know what was in here, we could do an IR. The IR may show a carbonyl and sp3ch. There could be thousands or compounds like that. If we do the mass was, 56, then we really start narrowing down what possibilities for the compound are. In addition to getting the mass of the molecule, mass spec also gives fragmentation, and we also interpret the fragmentation. And here we will really be interpreting the fragmentation. On the opening page, it talks about how they are now using mass spec to detect cancer, sort of very directly. Back of that is 2 IRs. Both of these are alcohols. You see the structure at the top. Can you assign structure to spectrum? Which alcohol is the top one?
One of them.
Both IRs show an OH. Both IRs show saturated sp3ch. Now the fingerprint's different, but unless you have a known spectrum to match with one of these, you can't tell. It's like trying to match a fingerprint of a criminal. You can't tell unless you had the fingerprint on file to match it up. I don't know which is which. Maybe if you had like a PhD in IR spec, you maybe could tell. But it's very difficult. On the other hand, those 2 alcohols have different masses, and a mass spec would easily tell them apart. On the next page is indeed the mass specs of 2 alcohols. I'm not even going to try to erase, guys. It won't work. The one at the top is your propanol, 1 propanol. The OH is at the 1 position. 1 propanol has a mass of 60. You can add it up. When we add these up, we're going to be using just the whole number. Carbon is 12, oxygen is 16, sulfur is 32. Some elements, though, have major isotopes. We need to be aware of that. You add the formula up, you get 60, just a whole number. This is called low-res mass spec, just whole number. We may talk about high-res mass spec where you can get like 3 or 4 decimal places. But mainly what we're going to be doing is low-res mass spec, just whole numbers. Here's an example of mass spectrum. Numbers at the bottom is essentially going to be our molecular weight. The true unit is m to z. That's mass to charge ratio. But if your charge is 1, then that number correlates with your mass. And most often your charge is 1. So most often this is your mass. This is just relative intensity of peaks. What we have here is peaks that occur at certain positions. And so this appears to be a very predominant peak here at 31. The most intense peak is just plotted at 100%. Everything else is just listed relative to that. Your most intense peak is called your base peak. If we look at this, first off, there's 2 ways. We know structure. We know we're looking for 60 because that's it. If we know that, we can look and say, hey, we got a peak at 60. So something there is 60. But I talked about fragmentation. This molecule can fragment and give smaller fragments with smaller masses. When we do see 60, the 60 is called our molecular ion.
Basically, that's the whole molecule. As we'll see on the next page when we talk about what's going on here, everything is going to be ions. Everything will have a plus charge. So often that's called M+. It's your molecule with a plus charge. Whole molecule. If we look below, this alcohol has a mass of 74 if you add it up. If we look at 74, look for a molecular ion. You see anything? 73. Okay. No molecular ion. Sometimes your molecular ion is not going to be there. It's going to be rare for us. Usually we'll see it. We do see cleavage peaks though. The base peak is at what value? 45. Once we learn cleavage, standard cleavage, sites, positions, that one up there, this was 45, the other one was what, 30, 31? Okay. Basically this is sort of introduction, getting you acclimated to what our mass spec looks like. Once we talk some more, you can go back and look at that. And hopefully, once we get through here and you're ready to go, you can look at those two mass specs and say, yeah, obviously this is one alcohol and this is the other. Okay, what's going on when we do a mass spec? The molecule first has to be ionized. This is the chemistry up there. Here's the instrument. It's in a box, like most instruments are. Typically, you dissolve the compound in a solvent. Although modern day, you can do it just solid injection. Typically, you dissolve it. You inject it with a syringe, a needle, and there's an injection port. Once you get it in there, the compound has to be ionized. Typically ionized, variety of methods. The most common is just to zap it with electricity, with an electron beam. Okay? Electrons come in, hit the molecule, and they bounce off. It causes the molecule to emit an electron. So when the molecule emits an electron, the molecule now has what charge? Positive, because it lost an electron. Also, because it lost a single electron, and most molecules, all the electrons are paired, either lone pairs or bonding pairs. If you only lose one, that means you've got an unpaired electron remaining. So I show a plus and a radical. It's called a radical cation. Now, earlier I called it our molecular ion. The molecular ion is typically a radical and a cation, because it lost a single electron. The electricity from the electron beam caused it there. There are many different ionization methods. This is called EI, electron impact, EI. Somebody in like 2001 or 2 won Nobel Prize for a newer ionization method that works better for like proteins, large molecules. EI is sort of your old standard basic method. Once you get your molecular ion formed, it's positively charged. This is all under vacuum. Pulled through here, it's pulled towards the magnet. Because we have these negatively charged plates, so the positive is pulled through here. Only the positives. They then encounter the magnet, and then they're bent or deflected by the magnet. But here's where the mass comes in, because the degree of deflection by the magnet is based on what? The mass. Okay? Now, is it bigger the bigger the mass, is it going to be deflected more by the magnet or less?
Less.
I think that's right, less. That makes sense, right? Basically, that can be quantified. And then these, after they're bent, they hit a detector, but based on how much they're bent, we can quantify that and turn that into essentially the mass. By how much they're bent by the magnet, or deflected, or curved by the magnet. That can be plotted. Of course, this is lots of ingenuity that goes into here and getting a plot and calibrating that in that instrument design. But that's, of course, when you take instrumental analysis or something to design instruments like that. Only positively charged species will come through the system and will be deflected and will give peaks. Let's put that up top there. I mean, if you can't see. So, for example, let's look at this ether here. We subject it to ionization, like electron impact. We make the molecular ion. So we can show it like that. The little, something like this is sort of like a partial box. But it's a radical cation. It has a molecular weight, though. Its molecular weight is the same as the original, because the electron doesn't add to the mass. It's too small. Now, the molecular ion can go all the way through, be deflected, and you can get a peak that registers for 122. But that radical cation is also susceptible to cleavage before it hits the detector. It may cleave to give these two fragments, and then this fragment hits the detector and it registers at 107. Now, both may hit the detector, and so you get your molecular ion and a cleavage peak. Or maybe that cleaves so quickly that it doesn't survive and it never hits the detector, and that's maybe why your molecular ion doesn't show up. It's just too unstable, it cleaved, and all you got is cleavage peaks, or so-called daughter peaks. Now, when this cleaves, we'll state this. When a radical cation cleaves, what does it give? It gives a radical and a cation. Which one of the two show up in the mass spec? Only the cation. Only positive charged species show up in the mass spec. They're the only ones that are pulled through and deflected. The CH3 radical, you're never going to see any evidence of that in your spectrum. Okay? This is written as M plus minus 15. Why? Because we lost the methyl, which is 15. 12 and 3 is 15. That's a quick way to do it. Or you can add it all up and you can say 122 minus 15 is 107, so it's 107. But saying M minus 15 is a quick way to just say, hey, my original lost 15. Any questions about what's going on with mass spec? Questions? How do you know where to please? We're going to be looking at that. Since we're making cations, we're going to be looking for the most stable cations. We're going to cleave to give the most stable cations. Do you think you can predict the most stable cation? Would you rather form tertiary or primary? Would you rather form resonance stabilizer or non-resonance stabilizer?
Resonance stabilizer.
Okay. I think we're going to be good to go once we start doing it. That's why mass spec goes so well with resonance. Okay. Question?
Do you form the radical on the least electronegative, or does it's or how does it choose?
You mean the original radical?
Yeah.
Yeah, I don't really ever show the exact position of the radical. It usually comes from a lone pair. I just do it very generically, and I kind of show it on the side like that. It comes, yeah. It may show more precisely in the textbook, but I'm not going to get us into precisely where the radical is. We will look precisely where the cation is going to be. Okay, let's do some examples. Sort of like IR, I'll do examples of different compounds. One here is just a, what is that, hexane?
This hexane, fairly busy spectrum. What's the mass of hexane? 86. Okay, what is it? C6H14? 6 times 12 is 72, and 14 is 86. Okay. Do we have a molecular ion? Looks like it, yeah. That looks like 86. So that's just where the radical cation made it to the detector. This is really a massive charge. What's the charge of that? Typically plus 1. So that means that the charge is 1. So that means, what this means is it's 86 per 1. Now, if their cation had a charge of 2, what would the mass really be?
Half.
It would still be 86 over 2.
Be 43?
Should be double.
Is that the same ratio?
No.
No, double. 172.
172. Yeah. What do I think about that? Very rarely do you encounter species at the introductory level that have different masses than 1. But if you get into big molecules like proteins, those can have charges of 2 and 3. And because of that, this is not really your mass, but this is the mass per 1. Okay? So this is really a mass to charge. Because remember, when it's deflected, if they're all plus 1, then it's all the same. But what if you had 2 of the same masses, but this one had a double the charge? It'll be deflected more just because it has double the charge, where the mass was still the same. Okay? The deflection by the magnet is also depending on the charge. That's why we're going to have both here. Again, we're assuming everything's plus 1 for us. What's the base peak? 57, which is m minus 29. Why do I say that? Because it lost 29. Now, what did it lose? Methyl would be 15. What's 29? 29 is actually an ethyl, because that's 2 carbons and then 5 H's. That's an ethyl. And a propyl is 43. So it looked like it lost an ethyl to give that. This is not a good molecule because anywhere you cleave, you're going to get a primary cation. But let me just show you an example. If we take hexane, and we got a radical cation. Now, if it loses an ethyl, we can cleave here. And the way we're going to do this is we're just going to cleave it to give a 4 carbon plus a 2 carbon. Now please, if that's 6, this has got to be 6. Now, a radical cation cleaves to give what? A radical and a cation. If we're looking for 57, which one is going to be the cation? Here, here. Okay? So this would be 57. What would this be?
29.
It wouldn't be anything. It ain't going to show up.
That would be 30.
This is indeed 29, but does that give the peak right there?
No.
No. No. That's not going to give a peak in the mass spec because it doesn't have a positive charge. It could have cleaved the opposite way, and this could have been the radical, and that could have been 29 cation. And that's probably where the 29 came from. Basically, that's a primary cation. In this example, there's no way to get a good cation. Basically, this thing can cleave all types of places because there's no selectivity. That's why you got lots of peaks there. So it's really not a good one to sort of hone in on. But we do have some cleavages. Let's look at the one below. The one below, a lot less peaks. Wonder why. Here's the compound, mass of 114. Now,
Apparently there's no 114, or you would have been shown the 114 area. There is a 99. What's the base peak? 57, which is m minus what? Which is actually m minus 57. Okay. That's such a big number. Looking at the structure, can you envision cleaving a bond to give a good cation? Can you envision, what type of cation can you envision forming if you were looking for the best one? Yeah. Okay, everything we start off with is a radical cation. Then it can cleave. If it cleaved here, what would we get? We get a radical and a cation. 1, 2, 3, 4. Which one's more likely to be the cation?
The tertiary.
Right there, make that the radical. What's the mass of this? 1, 2, 3, 4. 4 times 12 is 48. 3, 3, 3 is 9. 48 and 9 is 57. There's 57. There's a peak for 57. I'm pretty confident that that's the structure that's giving rise to that peak. Why am I confident? Because what type of cation is that? Tertiary, most likely to form. Why is this kind of the only major peak? Because it's such a good cleavage spot. Where the one above, there was no good cleavage spot, so it kind of cleaved everywhere. There was no selectivity.
So if that's a good spot, why are there other peaks still?
Well, because it is a high energy process. You can get other. It's sort of like in the IR when you get all those peaks in the fingerprint. What are they for? Well, we could maybe explain it, but it take a lot of time. And there's other things maybe going on. Is there another way to cleave to get a tertiary cation?
Yeah.
What if we cleaved off a methyl? Just made that and lost a CH3 radical. This would be m minus 15, because we lost 15. What are we starting with? 114? 114 minus 15 should be 99. You got to pick at 99? Ah, there you go, right there. So it cleaves a little bit that way. Why did it prefer to cleave the other way, though? Did I erase it? Better. And so why is it better?
Because there's a tertiary cation.
They're both tertiary cations, but we can also look at the stability of the radical, because it's still, it was formed. Which radical is better, CH3 or this here? Radicals are electron poor. They don't have an octet, so they're stabilized. It's the same consideration as the cation. If these are cation, which would be more stable? This one, because it's got the carbon group. It's a more stable radical, and thus they cleave that way more than to give the quite unstable methyl radical. The next one has a chlorine, and then the one below has a bromine. With chlorine and bromine, we have to be aware that there's two major isotopes for each. Chlorine, two major isotopes are 35 and 37. Okay? Now they're major, that is, they're both significant. With carbon, carbon 12 is 99%, so we can just use 12. With chlorine, it's a 3-to-1 ratio, so it's 75%, 25%. 25% you can't ignore it, you're going to see it. You have to add it up where some molecules, actually that's the way it is. Some of the molecules have chlorine 35. If you add that up, you're going to get 78. But some molecules have chlorine 37. And those add up to 80. So you got two different masses for molecular ions. And if we look right here, we see 78 and 80 in a 3-to-1 ratio. Now see, if you were adding up the formula for chlorine, you would use 35.45. What is that number there?
An average.
That's an average, because if you're working with a molecule, you have an average of the natural isotope. Mass spec doesn't see averages, it sees exact molecules. So it either sees 35 or 37. This is called your isotopic pattern or signature for chlorine, 3-to-1. The base peak turns out to be, what, 43? That's a primary cation that I'm showing there. I don't know any other way to get a 43. It's apparently where it cleaved between the carbon and chlorine. We've got that cation and a chlorine radical. I mean, there's no way to get a tertiary cation or a secondary. It's got to be a primary. And while we wouldn't want to show a primary cation like in a mechanism, in mass spec, you can get primary cations. What is this here? First off, it looks like a 3-to-1 isotope pattern. This looks like it's got chlorine in it. I identified this as that cation, where it cleaved between the second and third carbon to give that cation there. That's actually resonance stabilized. Sure, resonance structure. Of course, if you add this up, you're going to have some with 35 and some with 37, and so you get your 3-to-1 isotopic signature there.
I have a question. Why is that one carbocation on the base if the other one's resonance stabilized?
That's a good question. I think below we'll see sort of the opposite.
Okay.
It's a good question. It may be that chlorine radicals are so favorable to form, and that sort of overrides the carbocation stability. Somehow I started with chlorine. Bromine has two isotopes, and they are pretty much a 50-50 natural abundance. They're 79 and 81. Okay? If you look at the periodic table, it'll say almost 80. It's 79.9, almost 80. That's because it's almost an exact average of 79 and 81. But mass spec doesn't see 80. It sees either 79 or 81. So your 1-to-1, that looks like bromine isotope pattern there. Main peak, base peak is what, 30, 35, 40, 43? Okay. And I identify that as, well, again, it's that primary cation. Didn't we have that on the previous one?
Yes.
Yeah. So, for some reason, it's likely to form the primary cations as opposed to the resonance stabilized there. But for chlorine, it gave it more than the bromine. Okay. From here, we'll look at different functional groups, and we'll get sort of more predictive. The standard prediction we're going to make is going to be called alpha cleavage. You're typically going to cleave to put a cation next to an atom with a lone pair. Why? Because if the cation is next to a lone pair, what can that lone pair do? It can do resonance or Okay, there's resonance there. So this is an ether, molecular weight of 74. Here's a molecular ion. By the way, what is this 75 here? Does carbon have an isotope?
Yeah.
13? What if one of the carbons was 13? What would that add up to? 75. I mean, that's an isotope pattern for carbon, but it's so small we typically ignore it, don't really talk about it, because it's only 1%. Where if it was bromine, it would be equal height, but it would also be 2. M plus 2. Okay. The main peak we're going to predict here is the one I assigned. If we cleave where do we want to make cation again?
Next to oxygen.
Next to an atom with a lone pair. So where do we want to make cation at? Right there? If we make cation there, it would be next to an atom with a lone pair. How do we get cation there? Do we cleave here?
No.
We cleave here.
Yes.
If we cleave there, what would we get? This plus a CH3 radical. Is that better, guys? Why is this a good place? Because we can now invoke or show resonance. Right? I stabilize the cation, use lone pair, and we would get boom, boom. There, only one lone pair plus charge on oxygen. This resonance stabilized cation. It's actually the major resonance structure because there's more bonds. What's the mass of this? M minus 15. What was the original mass? 74 minus 15. What we got? 59? Is that where the peak is? Yes. Yeah. That's the main peak you would predict here. That's called alpha cleavage. Because you're cleaving to put a cation. If you consider this your starting point, the first atom away is your alpha carbon, the alpha atom. And we're putting the cation originally one atom away from that lone pair. The alpha cleavage term is not strictly defined. That's what it's called here. Now, the base peak is 31. I'm not sure what 31 is. We could spend time trying to figure it out, but it won't be very predictive. The peak I want us to be able to predict is right there, alpha cleavage. What if we did alpha cleavage on the other side? It'd be the same thing. Okay? Let's look below. Boy, that's a nice clean spectrum. One major peak. At where? 43? 44. Molecular ion of 101. Looks like it's pretty much absent. Let's finish up here, guys. This is the first compound we've seen with a nitrogen. This is the first compound that had an odd molecular weight. Look at all the others. All the others were even. This brings us to the so-called nitrogen rule. If you've got an odd number of nitrogens, your molecular weight will be odd. If you've got 0 or an even number, your molecular weight will be even. Odd number of nitrogens, odd molecular weight. Think about it. H2O, 18. Ammonia, 1 nitrogen, 17. Also, your cations with an odd number will be even. Look back at all the previous cations. Previous cations were all odd. If you got an odd number of nitrogens, your cations will be even. That's the nitrogen rule.
Please make sure you can rationalize why this is formed. Why is that formed there? It's alpha cleavage. Cation next to a lone pair. There's another cation that you could show here. Yeah. Think about tertiary, what its mass would be, and see if you see it on the spectrum. Please also look at the next spectra. Please go through these so you can have questions ready. Look at what you look for, the alpha cleavage. Cation next to lone pair. Okay, guys. No sir, we have lab tonight. Tomorrow, seminar tomorrow at 1, maybe A through C. See you later, guys.